Hey, welcome to Passages in Applied Mechanics by Dr. Lorenz Garcia. Today, dynamics, and the law of a machine systems. Let us discuss some of the fundamental principles on which the operation of all machines is based, but, before, what is a machine? A machine can be defined as a mechanical device, sometimes also an electrical device, or even an electromechanical device, but let us consider just a mechanical device for now, consisting of one or more rigid components, designed, and used for transmitting force and motion and for doing work. The general purpose of machines is to augment or replace human effort for the accomplishment of physical tasks. We can say the fundamental feature of most machines is that a large load is moved, or a large resistance is overcome, by means of a relatively small effort. We are going to apply these principles to a range of elementary mechanical devices called simple machines. In general, then, a machine is a physical system using power to apply forces and control movement to perform an action. Machines can be driven by animals and people, by natural forces such as wind and water, and by chemical, thermal, or electrical power, and include a system of mechanisms that shape the actuator input to achieve a specific application of output forces and movement. Modern machines are complex systems that consist of structural elements, mechanisms and control components and include interfaces for convenient use. Examples include a wide range of vehicles, such as trains, automobiles, boats and airplanes, appliances in the home and office, including computers, water handling systems, as well as farm machinery, machine tools and factory automation systems and robots. Mechanical advantage and velocity ratio. All machines have an input side and an output side. The force exerted on the machine on the input side is known as the effort, F-E, the resistance to be overcome, or the force on the output side of the machine is called the load, F-L. Machines are usually of such design that by application of a small effort, a large load can be moved. Could you think an example? A very simple one, the lever. The lever is another important and simple device for managing power. This is a body that pivots on a fulcrum. Because the velocity of a point farther from the pivot is greater than the velocity of a point near the pivot, forces applied far from the pivot are amplified near the pivot by the associated decrease in speed. Machines are usually of such design that by application of small effort, a large load can be moved. The relationship between the load and the effort, which gives an indication of the advantage that can be obtained by using the machine, is called the mechanical advantage of the machine. Mechanical advantage is usually greater than 1, and it depends upon the type of machine which is being used and it varies with the load. In order to do work, both the load and the effort must move. In some machines the motion is linear, while in others is rotational. The ratio of the distance moved through by the effort on the input side, S-E, to the distance moved through by the load on the output side, S-L, is called the velocity ratio of the machine. Velocity ratio is usually greater than 1 and, unlike the mechanical advantage, is constant for a given machine. For instance, it depends only on the arrangement of moving parts, and is independent of the load. Ideally, the mechanical advantage of any given machine should be equal to its velocity ratio. However, for a real machine, the actual mechanical advantage is always less than the ideal, due to the presence of friction between moving parts such as bearings, or sliding surfaces. Work and efficiency. Whenever a force moves through a distance, the product of force and distance is the work done. On the input of a machine, the work done by the effort, W-E, and similarly, on the output side, the work done in moving the load is given by the ratio of the useful work done by the machine in moving the load on the output side to the work put into the machine by the effort on the input side is called efficiency of the machine. In many occasions, the symbol for efficiency is the Greek letter, eta. Since we already have the relation with mechanical energy and velocity ratio, eta also could be calculated as. Since a machine does not contain a source of energy, nor can it store energy, from conservation of energy, the power output of a machine can never be greater than its input, so the efficiency can never be greater than 1. Usually, efficiency is expressed as a percentage, and in the absence of friction, it should ideally be equal to 100%. In actual machines, of course, efficiency is always less than 100. As all real machines lose energy to friction, the energy is dissipated as heat. Efficiency is very often confused with effectiveness. In general, efficiency is a measurable concept, quantitatively determined by the ratio of useful output to total useful input. Effectiveness is the simpler concept of being able to achieve a desired result, which can be expressed quantitatively but does not usually require more complicated mathematics than addition. Out of curiosity, this draw represents a scientist using a steam machine with pulley to extract a tooth from a man. It is a pen drawing picture by C.E.H. created in 1894. Friction effort. As mentioned, if the machine were perfect, no work have to be done against friction, and the efficiency would be 100%. This would mean that for a perfect machine, or that the ideal mechanical advantage is equal to the velocity ratio, m/a equal v/r. It also means that if there were no friction to be overcome, it would take a smaller effort to move the same load. The effort required to move a given load Fl, if the machine is 100% efficient, is called the theoretical effort, Fth. Substituting into m/a equal v/r, we have the difference between the actual effort Fe, and the theoretical effort Fth, is the effort wasted in overcoming friction and is known as the frictional effort, Ff. The law of a machine. The law of a machine is an equation which expresses the relationship between load, Fl, and effort, Fe. In many cases this relationship, when plotted as a graph of effort against load, is a straight line. Its mathematical equation is of the linear form, where Fe is the effort, Fl is the load, A is the slope of the graph, and B is the value of Fe, where the graph butts the Fe axis. The law of the machine can be used to predict the effort required to move any load by the machine. Limiting efficiency. If we calculate and plot efficiency for the experimental results under different load conditions, we will find that the efficiency increases with the load. However, the increase is not proportional to the load. There is a limiting value to the efficiency of a particular machine which is always less than 100%. The value of the liming efficiency can be found by combining the law of a machine with the definition of efficiency to have this expression: a machine has high efficiency if most of the power supplied to it is passed on to its load and only a fraction of the power is wasted. The efficiency can be as high as 98% for a large electrical generator, but it is likely to be less than 50% for a screw jack. Reduction of losses, such as those due to friction, makes a machine more efficient. Let's apply these concepts to solve engineering problems. Dr. Lorenz Garcia here, thanks for watching. Ciao.